So we continue with a quick revision of the number system. The main concept that is now introduced is the idea of an irrational number. Now it's going to be very easy to define what's an irrational number. An irrational number is a number that is not rational. Okay, so in other words, a number x is irrational if it cannot be expressed in the form of p by q, because q implies that the number can be expressed as a fraction p by q, and x cannot be expressed as p by q if x is irrational. So it's a fairly straightforward definition. So now let's just summarize our present understanding of the number line. You have numbers, natural numbers 1, 2, 3. Add a 0 to them and it becomes the whole numbers, and add the negative numbers to them and it becomes integers. And we also saw q, which are basically fractions. For example, half, okay, is a fraction which can be expressed as p by q, and it is a rational. And now the rest of the numbers are irrational on the number line. So we write the number line as r, and r is basically the rationals along with the irrationals. So the first question that comes to our mind is, are there examples of irrational numbers? And in your book, there is a few nice examples on the next page. So I've just highlighted the examples that I mentioned in your book: square root of 2, square root of 3, square root of 15. And there's also one very interesting example here. So I'll just write it down: 0.1, then 10, which is then there are 2 ones, then another 0, and then there are 3 ones, then another 0, and there are 4 ones, and the pattern goes on forever. So this is an example of a irrational number. So the question at this stage is, why are these irrational? Or why are these numbers in this page not rationals? So now this question can be answered by an interesting property of rationals when expressed in their decimal form. So you take hold of any rational, and there are some nice examples that are given, and express them in their decimal form, and we come across the key property of rational numbers. And that will tell us why this particular example is irrational. Those of you who already know the answer will know that this is an infinite decimal and not recurring in any pattern. So we'll try to understand what this means by going through the decimal representation of rational numbers. So we go to the next topic. But before that, can you locate the other examples? First of all, can you prove that root 2, root 3 are irrational? And I'll just utter the magic word here, which is proof by contradiction. Very interesting. And so I'm sure you know this, but we'll get back to this some other time, and that'll prove why root 2 and root 3 are irrational, or as we've been highlighting, not rational. So we prove by contradiction that these are not rational, and therefore they have to be irrational. Now in this particular page, deals with how to mark off square roots of natural numbers, root 2, root 3, and root 4 is just 2, then root 5, and so on. It's a very interesting construction, but fairly simple to understand. So we'll move on and come to the main idea, which is the decimal expansions of fractions. So the main idea here now is decimal expansions of rationals. And the book studies these with some simple examples. I'm going to highlight these examples that the book considers: 10 by 3 and 7 by 8 and 1 by 7. Basically, you are encouraged to actually divide and express these numbers in decimal form. And let's see what happens. So what happens is, on the next page, so here are the answers. The first one gives you 3.333, the next one gives you 0.875, and the next one gives you 0.142857, and then it repeats 142.857 and so on, and this is sometimes written as 0.142857 recurring. This is also recurring. 3.333 goes on forever, and this is written as 3.3, where 3 is recurring. Now, this is an interesting example. Here the recurring number is 0. And when the recurring number is 0, this one here, then we just call this as terminating decimal. Terminated decimal. So, the main conclusion is that any rational number, if R belongs to Q, and if it is expressed in decimal form, it is either terminated, or one can terminated or recurring. Now, it is not difficult to understand by these few examples why you would expect recurring. Why would you expect recurring is not at all difficult to understand. I'll leave it to you. But in particular, if the recurring number is 0, then we say that it's a terminated decimal. So, our final conclusion is that, maybe it's worth writing down on the next page, that either when you actually divide, the remainder becomes 0, and then you have a terminated decimal, or the remainder never becomes 0, but there is a recurring decimal. And this helps us to define irrational numbers. Irrational numbers are neither of the above. So it's neither a terminating decimal nor a recurring decimal, which means that irrational numbers are decimals without recurring of any pattern. And now you see why the previous example was a very interesting example. So I'll just write it down on the next page. So this tells us why a number like 1.0101101110111 and it goes on forever is very cleverly constructed to be neither of the above, and therefore this is a irrational number because it's not rational. Okay, so now we will, in this particular page, let's talk about the reverse problem. Reverse problem, which is that I'll give you a terminating decimal. So I'll just go and use the example straight away. So here is a terminating decimal. Can I make it a fraction? So this is very easy. So here's the example. It says 3.14268 is a terminating decimal, which means that the remaining decimal values are all 0. And this can of course be written as 3142678 divided by 1, 2, 3, 4, 5, 6 divided by 10 raised to 6. And if one can cancel some common factors, but essentially it's of the form p by q. How about these two examples, which are recurring? And our understanding now is that this is a rational as well as this is a rational. So can I make it into the form p by q? So let me just do both the problems very fast. These are nice, well-known problems. I might be doing exactly as the book or slightly different. So our problem is x is equal to 3. Okay, not 3, I'm sorry. It's 0.33333. And can I change it into a fraction? So what I could do is write it as multiply both sides by 10, and this becomes 10x is equal to 3.3333, and I'll call this 1 and call this 2, and 2 minus 1 gives me 9x is equal to 3, and this gives me x is equal to 1 by 3, which is what I've been trying to do, trying to make this as a fraction. Let me try this example as well. These are very simple but very important examples. So let me try also this problem. So I think I want to stick to this board. So I'll use this eraser and do this problem. Okay, what's the problem? All the illustrated examples seem to be extremely well chosen. So the problem is x is equal to 1.272727 and go on forever. This is x is equal to 1.27 recurring. So this time I shall multiply both sides by 100. So 100x is equal to 127 and 27 recurring. And once again, I call this as equation 1, call this as equation 2, and 2 minus 1 gives me 99x is equal to 126, and this implies x is equal to 126 over 99. I see that there are some common factors, but I'll leave it as the problem solved. Now there's one more example here, and I do not want to, these are all interesting, and I think these are all examples worth a visit from you. So I'm also trying to go ahead and do this problem. So x is equal to 0.235 35 and then 35, which is the same as 0.235 recurring. So like I said, there is a possibility that I might be slightly different in my solution. but there's essentially the idea is the same, whether you look at the book or look at how I'm trying to explain. So this time I'm just going to do it in 2 steps. Okay, so first I shall multiply by 10x, 10 on both sides. So 10x is 2.35 recurring, and now it looks very similar to my previous problem. So the only slight difference, and why I really wanted to do this problem, is because it's best done in 2 steps. So this is step 1, which takes it to looking like a problem that we did on the previous page. And now I'll multiply both sides by 100. So this becomes, so this is step 2 now. So the problem is best done in 2 steps. So this time I multiply both sides by 100. Okay, just call it equation 1. And then I multiply 1 with 100 because there's 2 digits being recurring or repeated. So 100, and so this gives me 1000x is equal to 235, and then 35 recurring. And then again, this will be called equation 2, and 2 minus 1 gives me 990x is equal to 233, and this gives me x is equal to 233 by 990. Yeah, looks like I got it right. So what is the moral of the story? The moral of the story is that given a terminating decimal or a recurring decimal, I can get it to be expressed as, I think I should not have used x here. I'm sorry, even the book uses x. Might be nice to use r because it's a rational. So the rational number very neatly expressed in the form of a fraction. Right. Now there is still one more idea which is there in the book. Very nice idea. So let's get to that. And this is very nice. Okay, and we shall use the idea. I shall remind you of this example of an irrational. So let's see again. So here's an example of an irrational. I'll just remind you 0.1, 0.11, 0.11, 1, 0, 1, 1, 1. We are now convinced that this is irrational. There is nothing special about this pattern. You can come up with many patterns which are not repeating. This is just a nice example. So there are definitely infinite number of irrational numbers. And this is the final interesting problem in this chapter. So, and then I'll repeat, I'll add one example to this, but let's come to that a little bit later. So the problem says, I'm referring to the problem here, try to find an irrational number between 2 rationals. Okay, there is nothing special about 1 by 7 or 2 by 7. In between every 2 rationals, we can find an irrational. I think that's the take-home message. So let's see this. Let me just write it. Between any 2 rationals, we can find an irrational. So that's the message of this problem. It's a very simple problem, but this is the nice take-home message of this problem. Okay, so let's do the problem. We have a rational R1, which we are calling it as 1 by 7. We have another rational R2, which we're calling it as 2 by 7. When we just did this, so I remember it by memory now. This turns out to be 1, 4, 2, 8, 5, 7, and then it keeps repeating 1, 4, 2, 8, 5, 7. And this is R2 is just 2 times R1, so can just multiply this by 2. So 7 to the 14, 1, 5 to the 10, 11, 1, 8 to the 16, 1, 17, 1, 2 to the 4, 1, 5, 8, 2. Okay, so this is 2 by 7, which is this recurring. Okay, so can I find an irrational? So I just want to tell you that I'm going to use this idea, which seems to be a very cool construction idea. So what I'll do is I'll first, let's call it x. I'll first find a number which is clearly more than R1's. So let's start with 0. Okay, let's write it here, 0.15. So really, clearly 0.15 is already more than R1. And now I'll just, and it is definitely less than R2. And now I'll just simply pad up into an infinite decimal in the same way. So 0, 1, 0, 1, 1, 0, 1, 1, 1. And you can see that x, R1 is clearly less than x, is clearly less than R2, and x is definitely irrational. X is definitely a real number which is not a rational. That's how you write it. Irrational numbers, very stylish way of writing it. So finally, there is one more case which is not discussed here in this particular book, but I think it follows by using the same strategy. Given any two irrationals, we can easily fit in a we can easily fit in a rational number and you can just go through the previous problem and use the same idea, use the same trick to convince yourself that this is true. And why only one rational? We can actually fit in infinite rationals. So, and pretty much with the same in the previous problem, given any two rationals, why only one irrational? We can fit in infinite irrationals. So on this interesting note, we stop the chapter on numbers, and I shall try and get another video up on the next chapter, which is on polynomials. Till then, goodbye, and I hope to see you soon again.